All right, let's get started. Here's some matrices. They're representing linear systems of differential equations. Often you'll just be given a matrix and it'll be like, do a thing with it. So the thing we want to look for here is just, is the system stable or unstable? They're not even asking us if it's a stable node or an unstable node or a stable spiral or an unstable spiral or a saddle, right? They're just saying, is it stable or unstable? And there's a reason we're talking about this right now, which we'll come back to after we get around the um the nonlinear systems of differential equations. There's a reason we can't talk about this. So let's go ahead and kind of look at this and then we'll talk about some things. So if we find the eigenvalues here, the determinant of a minus lambda I is equal to, let's see, the determinant of -3 minus lambda, -1, 1, -6 minus lambda. If we look at this, we're going to get -3 minus lambda times -6 minus lambda minus minus 1, which is going to be, let's see, lambda squared plus 6 lambda plus 3 lambda is plus 9 lambda. And then plus 18 plus 1 is plus 19. We're going to stop as soon as we can. So if I start finding my eigenvalues, I'm going to get lambda equal to, that doesn't factor, so it's going to be -9 plus or minus the square root of 9 squared minus 4 times 1 times, I don't know why I have, yeah, times 19 all over 2. And I claim that we can stop it. Well, let's do one more step. 9 squared is 81. 4 times 19 is 4 less than 4 times 20. So it's 80 minus 4, which is 76. So we have -9 plus or minus the square root of 81 minus 76 all over 2. Now here's where I'll point out in a minute. We could have stopped much earlier, but we'll get to here. So at this point, we can see that both eigenvalues have to be negative. -9 plus root 5 is certainly negative. -9 minus root 5 is definitely negative. So these are both negative, which means we have stability. You could think about the fact that we have a stable saddle, a stable node, if they're both negative and real, but really we just need to know that we have stability here. So for this matrix, we have stable equilibrium. So what I really kind of point out before doing these next two is there's less you have to look at if you're just being asked about stability. All we really need to look at is whether or not, well, first of all, if we want stability, we don't want to have a saddle. And I know it's been a minute, but we talked before about how the only time you get a saddle is if the determinant of the matrix is negative. So we only get a saddle if the determinant of the original matrix is negative. If that's not true, then there's still one other thing that has to be true. So let's say that the determinant's not negative. So on the other hand, if the determinant is positive, well, then you can have one of two things happening. Well, you could have one of four things happening, really. But the things that can happen are either you can have both positive eigenvalues, both negative eigenvalues, or both eigenvalues being complex with a positive real part, or both eigenvalues being complex with a negative real part. And two of those situations lead to stability, two of those situations lead to instability. Let's write out the equations. So here's what this is all really coming down to. Bless you. Sorry. With I feel like there's a thought there that I mean to finish and I'm not quite getting there. I'm sorry. So here's what I'm trying to get around to saying in the longest way possible. Your eigenvalues look like this. It's the trace of the matrix plus or minus the square root of the trace squared minus 4 times the determinant, which we often use that symbol for, over 2. What I really, 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 really want you to know is the following. We have stability or a stable equilibrium if both the determinant is positive, right? Because if the determinant's negative, we get a saddle. And the reason we get a saddle if the determinant's negative is because this part here, this square root of all this, becomes bigger than whatever this number is. So you're adding something bigger than it and subtracting something bigger than it. And one of those things is going to end up being positive, one of them's going to end up being negative. So whenever your determinant's negative, you get a saddle. But if your determinant's positive, the other four things can happen. And so the other thing we need is the trace to be negative. If the determinant is positive and the trace is negative, then your eigenvalues will either end up being both negative or complex with a negative part, a negative real part. So these are the two things we need for stability. And we typically say it is unstable otherwise. And I know I'm getting a little bit ahead of myself, but I'm just trying to set us up for something we're going to see in the future. I will also refer you to a picture that I mentioned that's in the textbook that I think is actually, let me, instead of saying the picture, let me show it to you instead. Sorry, one second here. No, except I don't have it teed up here. Let me think if I know where it is real quick. Oh, you know where it is? It's in our campus. Sorry, one second. This will take just a moment, but I do think this picture is worthwhile for all of you to at least have an idea of because it shows you something kind of neat and more important, meaningful. Where are you, book things? There we go. So looking over here in chapter 10 of our textbook. Yeah. Sorry, I know. I know. So what I want you all to see is this picture that I was going to draw, but I've drawn before, and it just looks better if we look at it here. Not those pictures. Almost there. Eventually. Someday. There it is. That picture right there. So that picture talks about the relationship between what you have for the trace and what you have for the determinant. So if your determinant is negative, if you're below this axis here, you're down here in saddle land, right? Whenever your determinant is negative, it doesn't matter what your trace is, positive or negative, whole thing's going to be saddle because your eigenvalues have to be opposite values. On the other hand, if your determinant is positive and you're up here, well, then a few different things can happen. But the determining factor for whether or not we have stability is if your trace is negative, then you either have a stable node or a stable spiral, but you have stability. If your trace is positive, you either have an unstable node or an unstable spiral, but you have instability. And finally, if your trace is zero and your eigenvalues are complex, then you have a stable, a neutral spiral, which I don't know what to say about the stability of a neutral spiral. I meant to look it up, and I just, as I'm saying, I'm like, oh yeah, I was going to look it up and totally forgot about it. Now, I will point out this picture is in your textbook. It's on page 650. I think it's worth looking at. I think it's worth remembering specifically you have stability in the upper left corner there. So if your trace is negative and your determinant is positive, you have stability, and otherwise you don't. So with that in mind, looking back at these other two examples, for our matrix in our second example, oh, you can't see what I'm writing. 1 second. I do, thank you. Our second matrix, instead of doing all the work of finding the eigenvalues, which again is not that terrible, but we can just go and say, hey, the determinant of this matrix is 1 times 4 minus 2 times 3, which is -2, and we're done. We know that since our determinant is negative, we have a saddle. We have instability. We have an unstable equilibrium. Specifically, we could say it's a saddle. And for our third one, which was following matrix, 1, 5, -3, -6, our determinant's going to be 1 times -6 minus 5 times -3, which is -6 plus 15, which is +9. And then we are going to look at the trace. The trace of our matrix is equal to 1 plus -6, which is -5. So in this case, we are in that upper left corner of the system where our determinant is positive and our trace is negative. So we have stability or a stable equilibrium. Now, to know if it's a stable node or a stable spiral, we would have to determine whether our eigenvalues were real or complex. In other words, is the discriminant of our quadratic formula going to have a real part or an imaginary part? Is it going to be square root of a positive or square root of a negative? But they're not asking us that, so we shouldn't really do it. But if we wanted to, we could say, well, if I actually write this out, we have our 1 minus lambda times 1 minus -6 minus 5 times -3. And then actually writing out the equation. That's not the way. Wow. Let's try that again. It should be 1 minus lambda times -6 minus lambda minus 5 times -3, which gives us the equation lambda squared minus 1 plus 6 is going to be plus 5 lambda. And then we have -6 plus 15 is +9. I could have skipped doing that, by the way, right? Since I already knew the trace and the determinant, I could have said, oh yeah, my quadratic formula is just lambda squared minus the trace times lambda plus the determinant. That's my quadratic equation. I see that my quadratic formula. So in this case, we're trying to check to see if it's real or not. So we really just care about what's the square root of 5 squared minus 4 times 9 going to do for us. I think that's going to give us an imaginary eigenvalues because that's going to be the square root of 25 minus 36, which is the square root of -11. That shows me that my eigenvalues had to have been complex. So we know it's a stable because we know it's stable already because our determinant was positive, our trace was negative. And we know it's a stable spiral because we have complex eigenvalues. Again, we weren't asked to do this. We just decided to do it. We being I just decided to do it. Okay. Again, at this juncture, we're not really doing it this way, but I'm just saying once we get to the nonlinear differential equations and trying to test for stability, we only really talk about stability or instability, and we don't actually say it's a saddle or it's a node or it's about because it's only what's happening locally instead of what's happening big picture wise, because there's multiple things happening at different equilibrium points. Again, that's a little bit in the future, but it just kind of, I felt like it made sense to talk about it right now because we've kind of talked about this stuff. That said, before we get there, we should talk about the non-homogeneous linear systems of differential equations, which the good news is they're not any harder than the regular ones. The bad news is sometimes we make it hard kind of without good reason, I feel like. But, well, I should say we make it harder so we can figure out what's going on and then we can talk about how it's easier. So let's say we're going to look at this system, this non-homogeneous linear system of differential equations. So here's our first two differential equations. We have dx1 dt equal to -x1 plus 4, and dx2 dt is equal to x1 plus 2x2. And what I want to point out right away, it's a terrible look at, so I really want to point out. Okay. So what I want to point out is 0, 0 is not the equilibrium here. If you plug in 0 for x1 and 0 for x2, you don't get both derivatives equal to 0. So typically, well, I should say before we do that, let's rewrite this as a matrix equation. So rewriting as a matrix equation, we're going to have the derivative of our vector x equal to the coefficient matrix. Now be careful here. Our coefficient matrix is -1, 0, 1, and 2. In the first column, coefficients of x1, in the second column, coefficients of x2. And then we're going to add on, oh, sorry, we're going to multiply that by x1, x2, sorry. And then we're going to add on the part that's making it not homogeneous. The constant 4 here, and there's a no constant there, so it's 0. So that part right there, that's the part that's kind of giving us trouble. Typically, when people write this out as a matrix, like just not actually writing the things, we write this as the matrix A times the vector x plus this extra non-homogeneous part B. So we're going to find the new equilibrium. So first, find the new equilibrium, which is still not that terrible. It's just setting both equations equal to 0 and finding this new solution, which isn't going to be 0, 0. Okay, not too bad. We set -x1 plus 4 equal to 0 and x1 plus 2x2 equal to 0. The first equation we can solve immediately. We get x1 equal to +4. The second equation, if we plug in 4 for x1, we have 4 plus 2x2 equal to 0. We get 2x2 equal to -4. We get x2 equal to -2. So that's our new equilibrium. Oftentimes we write this with a hat notation. So we'd say that our equilibrium is going to be x1 hat equal to 4 and x2 hat equal to -2. Okay, so this is our, yeah, sure, which will, or we can call this x vector hat is equal to 4, -2. So here's what we're going to do now. We're going to do a bunch of work to show us that really we could have just looked at this original matrix to find all the things we needed anyway. So the end result's going to be essentially that if we had looked at this matrix and kind of ignored this part over here, we could have just found the eigenvalues and the eigenvectors for this matrix and then done a little kind of twist at the end to make it all work out. But there are some steps that get us there. And what we typically do is we say, okay, we're going to set up a new system of equations. So our new system of equations that have 0, 0 as the equilibrium. So we're going to call these y1 and y2 instead of x1 and x2. So here's what we're going to have. We're going to have that y1 is equal to, I guess I'm doing it kind of backwards. I guess we say, sorry, let me do it the right way. First, you start off by saying that x1 is equal to y1. I feel like I wrote something wrong in my notes here. Make sure I'm not doing something crazy here. Yeah, I did. Okay, yeah, let me make sure. No, I'm just getting it backwards. Okay, I'm sorry. I'm just a little bit crazy. So we have y1, apologies, is x1 minus 4, and y2 is x2 minus 2. And we'll deal with that in a minute. Sorry, we got off track there. So all we're doing is we're taking the x's, subtracting their equilibrium to get the y's, which will now have an equilibrium of 0, 0. I know that sounds a little bit funky, but just hold on for a second. So all I'm saying here is that whatever my new system of equations is, it will essentially have the same stuff as my old system, but my equilibrium is what we want it to be. It's 0, 0, which we're used to having because we know how to deal with that. So we're going to do a couple things here. We're going to solve for x1 and x2, which is not hard to do. x1 is going to be y1 plus 4, and x2 is going to be y2 minus 2. And now we're going to look at our system of differential equations. So I'm trying to get back to this place here where I have my derivatives equal to some stuff just so I can kind of see what my new system looks like. So I'm going to find my derivative of y1. Well, the derivative of y1 with respect to t, if I take the derivative of this side, it's the same as the derivative of that side. So that's going to equal the derivative of x1 with respect to t minus 0. And similarly, the derivative of y2 is going to equal the derivative of x2. But we know what these two things are equal to. dx1 dt is equal to negative x1 plus 4. dx2 dt is equal to x1 plus 2x2. But now we're going to change these things to being in terms of the y variables. So this is going to equal, I'm going to plug in y1 plus 4 for x1. You get negative y1 plus 4 plus 4, which is going to be negative y1 minus 4 plus 4. In the same sort of way, I'm going to plug in y1 plus 4 for x1. I'm going to plug in y2 minus 2 for x2. And if we write this out, I'm going to get y1, I'm not going to write the plus 4, plus 2y2 minus 4, and the 4's cancel. So now we have a new system, and our new system is dy1 dt equal to negative y1 and dy2 dt equal to y1 plus 2y2, or written as the matrix dy dt equal to the matrix A, negative 1, 0, 1, 2 times the vector y1, y2. So essentially almost the same system, except now we don't have the oh my gosh, I keep wanting to say homogeneous, the non-homogeneous part over there, right? This system has a solution that is y1 equal to 0 and y2, or I should say, this system has an equilibrium, apologies, that is y1 equal to 0 and y2 equal to 0. So here, equilibrium is y1 hat equal to 0 and y2 hat equal to 0. And now we can go ahead and solve this in the usual way. Finding the eigenvalues, finding the eigenvectors, writing the general solution. Yes.
Know that y1 is always equal to dx1?
Yes, because here's the thing. So if y1 is just x1 plus or minus a constant, then their derivative, so if two things differ by a constant, their derivatives have to be the same. That's all. We're just kind of using, it feels like some trickery, to be honest. But we're just saying, oh yeah, y1 is x1 minus 4. So the derivative of y1 equals the derivative of x1 minus the derivative of 4. But that part is 0. Same deal here. If y2 equals x2 plus 2, then the derivative of y2 equals the derivative of x2 plus the derivative of 2. So the derivatives have to equal each other. Sure. So the way I'm getting the y1 and the y2 is I'm taking y1 is equal to x1 minus my equilibrium value for x1. So what I could have said here, what I maybe should have said here, is that we're going to always set y1 equal to x1 minus x1 hat and y2 equal to yx2 minus x2 hat. So then if x1 and x2 equal their equilibrium values, y1 and y2 will have to equal 0. Right? If x1 is 4, y1 is 4 minus 4. If x2 is negative 2, y2 is negative 2 minus negative 2, which is 0. So we're just kind of shifting things in a way so that our new equilibrium has moved over to the 0, 0 point. But the differential equations don't really change very much at all. They're still pretty much the same. So the rest of this is not terrible in that we've done it a few times already. We know how to solve a system like this. So to solve this system, well, in fact, we're blessed with a very kind of easy system here. Our matrix is negative 1, 0, 1, 2. We all already know the eigenvalues. The eigenvalues are +2, and -1. Not in any particular order. I just wrote them with the positive one first because I wanted to. And then we can find the eigenvectors, which are also not too terrible to find. So for lambda1 equal to 2, we have A times lambda1 equal to 2, sorry, equal to lambda1 times the vector. Oh my gosh, wow. I feel like my brain is not working. I'm writing the wrong equations all over the place. Sorry. We don't multiply the matrix by the eigenvalue, multiply the matrix by the eigenvector. So we should have A times V1 equal to lambda1 times V1, which writing it out is going to be -1, 0, 1, 2 times the vector we're looking for equal to 2 times the vector we're looking for. If you look at the first equation, you might feel like it doesn't tell you anything. -1 times x plus 0 times y equals 2 times x. But it does tell us something. If we have that -x equals 2x, we have to get the x is 0. There's no other choice. X must be 0, which means y gets to be 1. So our eigenvector here is the vector 0, 1. And that almost always happens when you have one of these matrices where it's really easy to see the eigenvalues, is that one of your eigenvectors is always either 1, 0 or 0, 1. In fact, if it's a 0 in the upper corner, it's going to be 0, 1. If it's a 0 in the lower left-hand corner, it's going to be a 1, 0. But you shouldn't remember that. You should just find it the usual way. For the other eigenvalue, lambda2 equal to -1, same deal, -1, 0, 1, 2 times our vector now is equal to -1 times our vector. And in this case, we should skip writing down the first equation because the first equation is -1 times x plus 0 times y equals -1 times x. And that doesn't tell us anything. Knowing that -1 times x equals -1 times x doesn't restrict what x can be at all. X could literally be anything. So could y, because y isn't even in the equation. So this tells us nothing. So we use the second equation, which tells us something useful. 1 times x plus 2 times y equals -1 times y. I'm going to subtract 2y from both sides and get x equal to -3y. So my eigenvector here is going to be, I would probably say that y is 1 and x is -3. But any multiple of that would also be fine. As is always the case with eigenvectors, any multiple is always fine. Okay, so now let's go back and find our solution. So our general solution here, the usual deal, your C1 e to the lambda 1 t times V1 your plus C2 e to the lambda 2 t times V2. So, but that's what our y is equal to. So we have that y of t, which is equal to y1 of t, y2 of t, is equal to C1 e to the lambda 1, which was 2t times V1, which was 0, 1, plus C2 e to the, why did I write lambda? Wow, that's a 2. I mean, I know I wrote lambda because I said lambda. E to the lambda 2, which is -1 times t times my second eigenvector, which is -3, 1. Okay, but then we have to go back to what x is because we started off with a differential equation in terms of x1 and x2, not y1 and y2. So very generically, what we do here is we add on the original equilibrium. That's what, so we're going to do the work to get there, but the shortcut here is to say like, okay, and then x is going to be the same thing plus 4, -2, because that was our equilibrium for x1 and x2. But let's see the work here so that you really believe it. So here's what we've got. Looking at this equation, my y1 is equal to C1 e to the 2t times 0 plus C2 e to the -t times -3. And my y2 is equal to C1 e to the 2t times 1 plus C2 e to the -t times 1. And we know what y1 and y2 are equal to. If we look way back at the beginning, we said that y1 was equal to not the beginning, I guess, x1 minus 4. And that y2 is equal to x2 plus 2. So we're going to just tag that in right here and say, great. This is equal to x1 minus 4. And this is equal to x2 plus 2. Well, then it's not too hard to take that and isolate x1 and x2. It's just going to be adding the 4 over and subtracting the 2 over. So that means we can say, I'm really out of order here. Yeah. That x1 of t is equal to y1 of t plus 4, which is going to be the c2 e to the negative t times negative 3 plus 4. And similarly, x2 of t is going to equal our y2 of t minus 2, which is going to be all that c1 e to the 2t plus c2 e to the negative t minus 2. Or written as a matrix, it's going to equal our matrix, sorry, our general solution, which was our c1 e to the 2t times our first eigenvector plus our c2 e to the negative t times our second eigenvector. And then we're just going to add on our x1 hat, x2 hat. So our solution for x of t, it's our typical general solution plus our new equilibrium. So all that to say, you could, in my opinion, completely skip the whole rewriting of things in terms of y or whatever variable you're choosing to use and just look at the coefficient matrix, ignore the other stuff, do all the work, find the general solution, and then at the very end, add on your new equilibrium. You do have to do the work finding the new equilibrium, but that's like not that terrible at all. So, any questions before we do another example? Okay. So in this, yeah. No, do I think that's what I want to say here? No. In this next example, we're going to do it this kind of shortcut way first, and then we'll go back and actually see that it still works if we do it the long way. I will point out, just so everyone can say it, so I will, just as a aside here, this system has a saddle. How do I know it's a saddle? My eigenvalues are positive and negative. But the saddle is now, instead of at 0, 0, the saddle's around the equilibrium for negative 2. Kind of interesting. So if you were to say, take the system of equations and draw the direction field for it using one of the graphing systems, you would see that everything, your saddle was centered around the point 4, negative 2, not around the origin 0, 0, which I think is just good to see. Yeah, let's look at another example so we can kind of hopefully see what I think is a faster way to approach a problem like this. So here's the next example. So let's say we're given the following. dx1 dt is equal to negative 2x1 plus x2 plus 4, and dx2 dt is equal to x1 minus 2x2 plus 1. And we're also given some initial conditions. We're given x1 of 0 is 0 and x2 of 0 is 0. So all that means is that we have to find the constants, right? If we see initial conditions, that's usually a sign for, oh yeah, we have to find C1 and C2. So I will point out at the origin, we don't have an equilibrium, right? If you plug in 0 for x1, 0 for x2, you get the rate of change of x1 being 4. And if you plug in 0 for x1, 0 for x2, the rate of change of x2 is 1. So we're going to find the equilibrium because we do need to do that. So we're going to set both equations equal to 0 and solve for x1 and x2. This one's going to be a little bit more work because it's not quite as easy. So if we set negative 2x1 plus x2 plus 4 equal to 0, and x1 minus 2x2 plus 1 equal to 0. I like an elimination personally, so I'm going to multiply this equation by positive 2 and add to that one. So if we multiply that by positive 2, we're going to get 2x1 minus 4x2 plus 2 equal to 0. If we add those together, we get 0x1, we get x2 minus 4x2 is negative 3x2, and 4 plus 2 is 6 equal to 0. So we're going to get x2 equal to 2. And then you can plug that back into either of these other equations. Let's go ahead and plug it back in right here. So we have that x1 minus 4 plus 1 is equal to 0. So x1 is equal to 4 minus 1, which is 3. So there's our equilibrium. x2 hat equals 2, x1 hat equals 3. So at the end of this process, after we find the equilibrium for the y's, which we're not even going to write down, but after we find the equilibrium, after we find the general solution for the y's, we're just going to add on the vector 3, 2. That's all we have to do to make it right. So our matrix A, well, it's just the coefficient matrix. It's negative 2, 1, 1, negative 2. So usual process for finding the general solution. Find the eigenvalues, find the eigenvectors. So determinant A minus lambda I is going to equal. Oh yeah, this one brings up something useful. So check this out for a second. When I write out this determinant here, I'm going to have negative 2 minus lambda times negative 2 minus lambda minus 1 times 1 equal to 0. And most of the time, I would say you should multiply this out and solve it the usual way by trying to factor. However, if you notice that your matrix has a diagonal where the two elements on the diagonal are the same thing, instead of multiplying it all out and then factoring whatever, adding the factoring, you can say, hey, look, I have something here that's squared. So you could take a shorter route and say, this is negative 2 minus lambda squared minus 1, add 1 to the other side equal to positive 1, square root both sides. So negative 2 minus lambda equals plus or minus the square root of 1, which is 1, and then solve for lambda and get add lambda over there, plus or minus 1 to the other side. We get negative 2 plus or minus 1 equal to positive lambda. So lambda is equal to negative 2 minus 1 and negative 2 plus 1. So it is a faster way to do this, whether or not they're real or complex, right? If this had been a plus 1 here instead of a minus 1, I would have a negative 1 on the other side, and then negative 2 minus lambda would equal plus or minus the square root of negative 1, which is I, and then you would still be able to solve for lambda in the same way. So if you see that where this and this are exactly the same factor, I think this is a faster way to go. But again, you can also multiply it out. Still work. So my lambdas are both negative, so we know we have a stable node. We weren't asked about that, but still good to observe. Let's go ahead and find our eigenvectors. So for the eigenvectors, lambda 1 equal to negative 1, we have the matrix negative 2, 1, 1, negative 2 times the vector we're looking for equal to negative 1 times the vector we're looking for. So let's see, our first equation is negative 2x plus 1y equals negative x. Add 2x to both sides, we get y equal to x. So the vector we're going to write down is 1, 1. For lambda 1 equal, for lambda 2 equal to negative 3. Bless you. We get negative 2, 1, 1, negative 2. Again, times the unknown eigenvector. Now it's equal to negative 3 times the unknown eigenvector. And now our first equation is negative 2x plus y equal to negative 3x. When we add 2x to both sides, we get y equal to negative x. So our eigenvector here is going to be, let's do the same thing I did before, 1, negative 1. Now the general solution. Now, for the general solution, even though I haven't done anything with x's and y's, I'm still going to write down y because I know it's the general solution for what I would have chosen y equal to. So my general solution is y of t is equal to c1 e to the lambda 1 times t times v1 plus c2 e to the lambda 2 times t times v2. Which then means so I will say, I don't think you can find the constants before you go back to the original variable. So then our x of t would be the same thing. We're just going to add on the 3, 2, which is our equilibrium there. So x of t is going to be c1 e to the negative t, 1, 1, plus c2 e to the negative 3t, 1, negative 1, plus that original equilibrium, 3, 2. Yeah, we got time. So let's go ahead and find our C values. So we have our initial condition, which again was that x1 of 0 equals 0 and x2 of 0 equals 0. So we plug in 0 for t and for our x and x1 and x2. We get 0, 0 equal to c1 times e to the 0 times 1, 1 plus c2 times e to the 0 times 1, negative 1 plus 3, 2. So then this ends up becoming the equation C1 times apple C2 is equal to negative 3, negative 2. Now, most of the time when we've been solving for C1 and C2, I've shown you kind of the most rudimentary way of doing it, which is just writing some equations down and solving. But you can actually use a matrix to solve this if you want to. You could say this part here is really the matrix 1, 1, 1, negative 1 times C1, C2. And we could say it's equal to, well, it's going to be equal to 0, 0 minus 3 minus 2. And it's still the same equation, right? This really just say 1 times C1 plus 1 times C2 equals negative 3, and 1 times C1 minus 1 times C2 equals negative 2. And then if you wanted to solve this, instead of doing like elimination or substitution, you could multiply both sides of this equation by the inverse of this matrix. It's another way of doing it. It's totally valid. Some people really like doing it that way. So we could say that C1, C2 is equal to, okay, to find the inverse of a matrix, I know it's of a 2 by 2 matrix, it's been a minute, but it's 1 over the determinant, which is negative 1 minus 1, which doesn't work if the determinant is 0, but it doesn't have an inverse of the determinant 0. And then, okay, you switch the diagonal elements, so they trade places, and the off diagonals get opposite signs of what they were. So instead of 1 and 1, I'm going to have negative 1 and negative 1. And then you multiply that by negative 3, negative 2. So multiplying this all out, we're going to get, let's see, 3 plus 2 divided by negative 2 is negative 5 halves. And 3 minus 2 is 1 divided by negative 2 is negative 1 half. Which is what I have in my notes, which is good. I did it a different way in my notes. So then finally, our particular solution here is and now again, I prefer to write it out as a vector. It's x of t, or if you prefer, x1 of t, x2 of t, equal to c1, which we found to be negative 5 halves, times e to the negative t times 1, 1, plus c2, which we found to be negative 1 half, times e to the negative 3t times 1, negative 1, plus 3, 2. When you say multiply, well, what do you mean when you say multiply it across?
C1 plus.
Like up here, like, yeah, like, sure, definitely to solve for C1 and C2, I could have just said, yeah, we have 0 equals C1 plus C2 plus 3, and 0 equals C1 minus C2 plus 2. That totally would have worked as well. And then we could do it by elimination. If we add these two equations together, we get 0 equal to 2C1 plus 5, subtract 5 divided by 2. Oh yeah, C1 is going to equal -5/2. And then you can go back and also find that C2 is negative. I was just trying to show you another way of doing it because sometimes the arithmetic here can get fairly messy, and sometimes it's easier just to find the inverse of the 2 by 2 matrix instead. But either way usually works. I said we were going to go back and then do it the long way. So don't think we have time to do all of that, but I'll just point out. So if we were doing this the long way, going back to where we started, our first step would have been to have said, okay, well, if our equilibrium looks like that, then we're going to say that y1 is equal to x1 minus 3, and y2 is equal to x2 minus 2. Which also then gives us, it almost feels silly that we write this all up, but we do. X1 equals y1 plus 3, and x2 equals y2 plus 2. And then we can see that the differential equations give us the same stuff, right? dy1 dt is just equal to dx1 dt. It really feels unnecessary to write this. And dy2 dt equals dx2 dt. And then remembering that, yeah, again, sorry. Remembering that dx2 dt, or dx1 dt, is equal to, let me miss a fact, -2x1 plus x2 plus 4. We can then plug in x1 and x2 here and get -2 times y1 plus 3 plus y2 plus 2 plus 4. And when you add it all together, you get -2y1, you get -6, you get plus y2, plus 2 plus 4. Oh, the -6 plus 2 plus 4 is 0. And in a similar way, this one equaling x1 minus 2x2 plus 1. Well, x1 is once again y1 plus 3. X2 is y2 plus 2. And if you add this all together, you get y1 minus 2y2, and the 3 minus 4 plus 1 adds up to 0. It always works out that way. So you almost never even have to check it. And then after we found our general solution for the y's, which was this, then we just go back and say, oh, but if the y's are equal to that, then the x's are just y1 plus 3 and y2 plus 2, which is why we're adding the 3 in the first row and the 2 in the second row. So really, I really think writing out all this first work here doesn't seem super necessary. But again, I'm not the one teaching it or the one who's studenting it. So you all should be more aware of what your instructor expects of you if you're covering this. Which again, I don't know if Arn's class is covering this. I do know that Lee's class has covered it. So there you go. I have office hours from 1 to 4 over in math drop-in. And yeah, for those of you I think in Varn's class, and some people had some questions about optimization. So please do drop on by if you have questions about optimization. I know we did that a couple weeks back in class. There are some videos of that if you're kind of getting stuck there. Yeah, all right, that's all I got. Free to go. Let's see. Yeah. And on Wednesday, we'll talk about nonlinear. Thank you.
Oh.
You're welcome. You too.
This side.
Let's see.
It was like, you know how the one that was like a high segue, but it was like still. Yeah, I didn't know how to.
You know, I just.
Yeah.
Or can you find the political outline?
Yeah.
Then they, then like.
And I'm not sure what we're saying here.
That's just
Oh, like how to find the eigenvector?
But I'm gonna.
Yeah, totally. I would, you can even put in the lambda there, yeah. Or you can do it this way, yep.
Are you going to?
Yeah, looks good.
Okay.
Yeah. I'll
And, this thing,
That, the determinant?
is this thing?
Yeah. We just, so yeah, we use this capital delta for the determinant sometimes and tau for the trace.
We're after each other for a little bit. Next week. Yeah.